Hello. For this weekend, I'll show you what I would do if I was to make a couple of study sheets. But after this weekend, you're expected to make your own study sheets, and I'm always happy to check them over. So far, I've checked over a bunch of flashcards, and I think we've made a lot of improvements on how to make and use flashcards. And I think some of you are trying to do the roadmaps yourself, which is great. I think you're going to find that things are going to be very easy to recall when you do your exam. But for this last weekend, I do want to show you how I feel like these topics can be put together. And so in this first page, I'm putting together and comparing the reduction and oxidation roadmaps, because I know that there are several reagents, and if it was me studying this, it's very easy to get confused. So I'm going to list first, before I put them onto a roadmap, the different reagents that I may see on the exam. And I'm doing this from memory, but you should do this from your lecture notes. And if there's a discrepancy between what you know to be real and true and your lecture notes, change it right now, okay? But in my opinion, what should be happening is you take your notes on your handout, and then you process that information in different ways, i.e. study aids, and then you transition to study aids. And you should be using those not only to study, but also to finish your homework notebook and to do practice problems, at least early on. Okay, enough with the setup. Let's look at the two main oxidation reagents, but not tollens. One of them has several forms. Okay, so the one that has several forms is chromic acid, H2CrO4, and you'll see that sometimes as CrO3, or I use a mixture of the sodium dichromate, if you can memorize that, with sulfuric acid. So that's number one. Number two is PCC. Okay. And for some of you, this is new, but I've hammered this several times in different classes. What's new for everyone is the reducing agents. And let me do that in green. And so reducing agents, I'm going to try to do this in order of how we learned it. We first looked at hydrogenation because we saw this actually in Organic Chemistry 1 to reduce carbon-carbon double bonds and triple bonds. But now we're going to use it to reduce aldehydes and ketones. So that's number one. Number two, I might get in trouble numbering, because number two is a two-reaction sequence, I believe. I believe LiAlH4 was next, followed with H3O+. Okay. Number three is the reducing agent, hydride reducing agent, that's not as strong, and you could mix it with water or methanol. I'll use water in this case. Number four, two of them are the same, so it's going to be number four and number five. Four is Clemenson. Clemenson is zinc mercury amalgam with HCl. And it does the same thing as number five, which is Wolff-Kishner, H2N NH2, that's hydrazine with KOH. And what do you notice down here? We have 2 arrows for the oxidation, 4 arrows for the reduction. Why not 5? Because we'll put these two together, or we'll mention them at the same time. So in purple, looks like the oxidations. The top map should be for oxidation. Okay. All right. Let's go to the left let's practice with the CrO3. And to the right, we have PCC. Now, this is, again, this is sort of what I would use as a study sheet, but you have to know, or you have to look in your handout and lecture notes, what does this oxidize? And so we have a couple choices. You're oxidizing the carbon, right? So you're either oxidizing this carbon, which is part of a secondary alcohol, to make, well, a ketone. You could oxidize this carbon, which is a primary alcohol, or you could oxidize, I know, not the greatest thing to do, but I'll put a dot in the middle of the C. Okay? I'm going to try to draw everything as line structures in my answer. And so, do we remember the more stronger oxidation agent? You're going to oxidize the primary alcohol, which is right here, to the carboxylic acid. And so let me take care of that first. I'm going to use my dot. And I know that got oxidized to the carboxylic acid. Okay. If you're having difficulty, I'm not sure why you're not using these tricks. Okay, they're meant to help you avoid errors. There's a dot, go down, and then let's go to the left, okay, to this other dot right here. So on that dot, we have a methyl group, and we have a secondary alcohol that is oxidized to the ketone. Okay, I mean, you could try to oxidize this dot into the carboxylic acid. You're going to have too many bonds on that dot. Because remember, when you oxidize, you also have to remove a hydrogen. And so there's only one hydrogen. Whoops. Let me do this in a different color. There's only one hydrogen here. Okay? So we could only oxidize it at the most once. Over here, we could oxidize that carbon at the most twice. And we did oxidize it twice. And this aldehyde group, you have this H. Now, at this point, maybe you're not, or because we're ready for the CHO group, maybe you're not seeing the CHO group properly. You have a scratch sheet of paper, or if you have room on your problem set or exam, you could redraw and get rid of the condensed structure. So we have this dot here, and that's your OH. Yeah, it's a little bit crowded. I don't like that. Let me just fix this. I've been doing pretty good on this video with my handwriting. Okay, no lines, no hydrogen. I'm not gonna draw it, but here's your dot. Here's your dot. Here's your third dot. Okay, so we are oxidizing now with CrO3. We're oxidizing the aldehyde. So it's this dot over here, which has one H to give up, and we will replace that H with an OH to make the carboxylic acid. Okay, look at PCC. PCC can oxidize the carbon up to a carbonyl group, but it can't oxidize anything to a carboxylic acid. And let's start with on the left. Let's go from left to right. This dot here, that's a secondary alcohol. And we could do one oxidation to get to the carbonyl group. Okay? PCC, you'll see the big difference between PCC and CrO3 at the primary alcohol. Because here, before we went to the carboxylic acid, now we only go to the aldehyde. Take a look at your notes. I emphasize that when we go from 1 carbon-oxygen bond to 3, we skipped 2, right? We went beyond 2, we went directly to 3. So what does the 1 carbon-oxygen bond to 2 look like? It's here to there. And PCC stops. PCC stops at the carbonyl group, okay? And so a kind of a trick question is, for this aldehyde that I drew, whoops, not dot, that I drew like this, nothing happens to it. It's already a carbonyl. And so just like this aldehyde stayed, or stayed after it was made from here, this one stays as well, unaffected by PCC. Okay, and that's the only difference for this molecule is this group up here, the primary alcohol. Oh, and also this one here, the aldehyde. It's not oxidized with PCC, but it is oxidized with CrO3. Now, some of you, and I think it was a great idea, is for each reagent, you list it in words, because if you could verbalize what functional groups you're reacting, it's going to be so much more easy to recall this on the exam, because you'll have that kind of background voice. Oxidize what? You're going to oxidize a primary alcohol to a aldehyde. Whereas for the CrO3, your primary alcohol goes to the carboxylic acid. So there's a major difference there. Secondary, for both of them, you go to the ketone. No difference, right? Go to the ketone. Tertiary, you can't oxidize. And then, yeah, we have that kind of tricky where we don't start with an alcohol, we start with an aldehyde. And yes, you go to the Ca again. I'm looking at this right here. Okay, for the PCC, aldehydes are not reactive with PCC or to PCC. So this is don't touch. Okay. It may not be necessary to put all of this information, right? If you knew everything in orange, go ahead and draw the final products, okay? And we could do the same thing for the reduction. What color did I use? Green. And I have these 5 reagents, but one arrow will contain both Clemenson and Wolff-Kishner. In order, from the left, going counterclockwise. Okay, so now I'm not using any notes. I already used my notes to get this list. You should be able to memorize this list pretty easily. And now we're putting them around the roadmap. NaBH4, water or methanol, and up here, Wolff-Kishner, or that's Clemenson, or Wolff-Kishner. Okay. You have now reduction. You are reducing possibly this carbon, possibly the carbons of the multiple carbon-carbon bond, this carbon of the carboxylic acid, this carbon of the aldehyde. Okay? Real quickly, again, if you're having trouble seeing this, the condensed structures, and I think some of you are, because when you draw your product, a lot of you are missing carbons because I'm not sure why you're missing carbons, but I think you'll avoid missing carbons if you draw it out and literally put a dot, because that dot has to carry through the reaction. And so, again, we have a little bit crowdedness, so I'll just draw the aldehyde like that. And so I'm putting dots for sure, okay? For instance, on this guy on the left, when I put the dot, I know I got to draw a methyl group, okay? And then I may or may not have to reduce this. Let's see what happens for the first reagent. Here's your dot. It has ethyl, and then that reduces to an OH. Not only do you need to know that this gets reduced, okay, you got to know what it gets reduced to, right? That's also, I've seen some problems with that. You're very good at, in general, figuring out which groups get reduced, but sometimes you don't reduce it to the right functional group. Okay, so where's our next dot? Our next dot is way up here. Nope. See? I caught my mistake by putting a dot there. Because to me, I could definitely tell that dot was in the wrong position here. And so we have a carboxyl group, and I'm looking at the blue right here, and that, H2PT does not does not reduce carboxylic acids. Don't touch it. Carboxylic acids, that's a good thing to note. Only one of these reagents reduces carboxylic acids, right? Maybe I could circle it here. Only the LiAlH4 reagents can reduce that carboxyl group. And so that tells me that this group will stay for this reaction and for this reaction. Okay, I think people are understanding this. Let's take a look at the triple bond. Whoops. H2PT does reduce carbon-carbon multiple bonds. And so, I'll erase that. Oh, that's why the dots are important here, because I have to make sure I have the right number of carbons. So the dot, look at the starting material. 2 dots and a methyl. 2 dots and a methyl. Okay. I hope. From this chain in the horizontal line, we have 1, 2, 3. 1, 2, and 3. Now this tro group, the aldehyde, looks like this, and H2PD does reduce aldehydes and ketones to the alcohol. And again, see the dot? If you did this, right, that's incorrect. That's incorrect because I didn't put a dot. If I use my dot technique, the dot's there, and then you have to make a bond from the dot because that dot has to be a carbon. Okay. If you want to pause the video, I should have told you this a long time ago. If you want to pause the video, we need to pause the video and try the other 3. Man, how do I pause this video? I'm choking here. Okay, lithium aluminum hydride is a strong reducing agent. Let's do this a little bit faster. It doesn't touch the carbon-carbon multiple bonds. It does reduce the carboxylic acid to an alcohol. There's my dot. Okay, here's the other dot. And then the aldehyde dot is here, and it gets reduced to an alcohol as well. Okay. And I don't know. Some of you who are not coming to my drop-in hours may not believe that it's that easy to lose or gain a carbon, but I keep seeing it, and I am going to insist that go ahead and draw the dot so you don't start gaining or losing carbons randomly. I always do it myself, actually, because again, it's very embarrassing for me to lose or gain a carbon when I'm trying to talk about a reaction in a presentation or to my colleagues. What's the difference between this hydride agent and this hydride agent? They're both hydrides. They're both delivering hydrides. The biggest difference is this cannot reduce carboxylic acid, so we are going to keep this untouched. Okay? Everything else gets reduced just like we did with LiAlH4. So I'm copying what I see all the way on the left, except for the carboxylic acid. I am going to make sure I do not reduce that. Make sure you have the dot, and that's where your carboxylic acid goes. Oh, now this one, for the zinc mercury amalgam and HCl and the hydrogen and KOH, this is where people are losing carbons all over the place. Okay, so don't lose the dots. Those reagents reduce the carbonyl group to a CH2. So I'm literally just removing the oxygen that was here. It does not touch, it does not touch carboxylic acids. Are you a little bit iffy on that? If you are, how fast can you find it in your notes? Where did we talk about this reducing agent? It's in the class where we talked about reducing agents, and it was the last one we talked about. Okay, so you should be flying towards that last page of that handout. Okay, and you could confirm that it does not touch carboxylic acids. It does not touch carbon-carbon multiple bonds. It does touch aldehydes. So your aldehyde dot is there, and you remove the O, this O over here, and you added 2 H's. But that's a methyl group. Shouldn't it have 3 H's? It does have 3 H's. There's one there already. Okay? And so the way I describe these reagents, the last two, is you go from a CO to a CHH. And now, if this was an H, then this is an H, just like in an aldehyde case here. Okay. Take a look at that. Yeah, it's good. I mean, I if I was to use this as a study sheet, I'd clean it up a little bit. I actually don't like how it looks on electronically. I would have this as a hard copy and use pens, but that's not too bad. That's all the reducing agents and oxidation agents you need to know in your life. It's all on one page. Okay? In the next video, we'll move on and we'll talk about, looks like hydrolysis of what? Of all the different heads on the totem pole.